Good question. I tried to work this out from the ripe age of 17, but it took me until my 4th year of undergraduate until I understood it fully. Here is the more technical answer on where it comes from and why James Clerk Maxwell managed to unify it with the electric force. One way to think about magnetism is that it is the relativistic correction to the electrostatic force. This is because all information, including the spread, continual update of electric fields as charges move, cannot travel faster than the speed of light. Thus, only moving charged particles feel a magnetic force in a magnetic field, and only moving charged particles can generate a magnetic field. If particles are not moving, you don't need to correct the electric field as no continual update is needed, so you don't need the correction, that is the magnetic field. This means magnetic materials are magnetic only because the electrons inside all move or spin in a similar way, meaning their magnetic fields add up. Consider this thought experiment. Feynman first suggested this experiment in his famous lectures on physics. Consider two equal wires carrying equal currents in the same direction. This might be a bit advanced, but they both have magnetic fields wrapped around them by the right-hand rule. As current is basically moving charge, they both experience forces by Fleming's left-hand rule. And thus they attract. We know current in wires is carried by electrons, traveling in the opposite direction to current because they're negatively charged, while the positively charged nucleus stays still. As the wires are neutrally charged, amount of negative charge equals amount of positive charge. All the force comes from the magnetic and not the electric force. Also, the nuclei are not moving, so they experience no force. We only need to think about the electrons to find the total force on the wire. Let us pretend we don't know what the magnetic force is and only the electric. How do we explain the attraction between the wires? If we do like Einstein does, and pretend to be an electron, what do we see? Now the protons are moving and the electrons are still. We're simplifying a bit things by saying all the electrons are moving at the same speed. But also, other weird things happen. Ever heard of length contraction or time dilation? Well, as the electrons are moving relative to the nuclei, they see the nuclei squish up in their frame of reference and the wire seems shorter. But as the electrons are all traveling at the same speed, these don't seem squished up. So now the density of positive charge is greater than the density of negative charge and the electrons see the wire to be positively charged. Opposite charges attract, so the electrons feel a force towards the wire and pull the wire with them. They don't feel a magnetic force in this frame of reference because they're not moving. This is where the magnetic attraction comes from. Time dilation just makes the size of the force numerically right. We also don't have to worry about the nuclei, as we already said they experience no force. You may ask, but aren't the electrons moving slowly, so relativity shouldn't really matter? Yes, they are moving slowly, but there are lots of electrons, so lots of small corrections add up to produce a noticeable force. Therefore, magnetism is just a simplified way of calculating this relativistic correction to the magnetic force without jumping between different frames of reference. It just so happens, because physics and maths are a bit weird, that the magnetic field, the magnetic force, and the motion of the particle are all at right angles to each other, Fleming's left-hand rule. In reality, all there is just the electric force and relativity when it comes to charged particles, ignoring electron spin. Bonus. In classical physics, gravity has its own relativistic correction, which is similar to magnetism. But this force is so small, Because gravity is so weak it's really only noticeable in really heavy things, like binary star systems. Also, there are more important corrections and these are all incorporated into general relativity so we never really talk about them.